All right. So hello everyone. Welcome to our COLING2020 tutorial. And our tutorial is about multilingual neural machine translation. And this tutorial will be given by Raj from ICT Japan, Zhenhui Chu, which is me from Kyoto University, Japan, and Anup from Microsoft, India. And here shows our tutorial materials. So we created a homepage so that you can check what we talked today on our tutorial homepage. And besides that, we also wrote a survey paper which has been published in the ACM Computing Survey, which has a very detailed review of multilingual neural machine translation. Besides that, because the field is very fast moving, so we also created an updated bibliography so that you can check the reference beyond the ones listed in our survey paper. And first, let me give a brief self-introduction of myself. So I'm Zhenhui Chu. I'm now working as a program-specific associate professor at Kyoto University. And before that, I was a research assistant professor at Osaka University and a researcher at JST and a research fellowship for young scientists at JSPS, Japan. And my research interests center on machine translation and language and vision understanding, and I have several projects related to these two research fields. And this is the outline of our today's tutorial. First, I will give a brief overview of multilingual neural machine translation in around 30 minutes. After that, my colleague, Raj, will give a detailed presentation about the Multiway modeling of multilingual MLMT. After Raj's part, Anup is going to talk about raw resource translation in multilingual MLMT in about another 1 hour. Then it will come back to me by introducing multi-source translation in about 10 minutes. And finally, I will talk about data sets, future directions, and summary in about 20 minutes. First, what is multilingual MLMT? Or in short, MLMT. So, our definition of MLMT is that it is the MLMT systems that can handle translation between more than one language pair. And this is actually a very active research field. And what is the research field? What the researchers in this field try to address is that they want to solve the problem about how can we leave gauge multilingual data efficiently in order to learn distributions across multiple languages so as to improve not just MLMT, but also natural language processing performance in general across all languages. So, why MLMT is important? Here shows a figure about the top 100 language pairs in the open source pairal corpus created by Tedman. So you can see that in the x-ray it shows the language pairs, and here the y-axis shows the corpus size. So we can see that for several language pairs, we have large pairal corpora, but for many others, they only have few pairal corpora. So we have a long tail even in the Opus data, right? So for high-resource language pairs, bilingual MLMT might perform well, but for this part, the low-resource MLMT, how can we improve the performance? That's a question. Let me show you another figure drawn by Google, a paper from Google. In their paper, they showed the same problem of the data distribution over language pairs. So here we can see that for language pairs such as French, German, or Spanish between English, so the target language here is always English. So for these language pairs, they have really a lot of pair sentences. Here is actually 10 million, right? So with 10 million of pair sentences, even a bilingual MLMT system can perform pretty well. But how about other languages? So we can see that here again, we have many low-resource languages here. For this language, low-resource languages, such as Yoruba, Syntactic, or Hawaiian, some of the language pairs even has less than 100,000 pair sentence pairs. Even you cross all the web, Google cross all the web to cross the pair sentences, right? You cannot get many pair sentences. So how to learn a good MLMT system for these low resource language pairs? Because there are a very imbalanced data distribution for different language pairs, we need MLMT. So that's the motivation of MLMT. So let me explain the motivation more formally. So MLMT systems, they are very desirable because, as you already seen, we have a lot of resource poor or low resource languages, right? And training models for these language pairs from many other language pairs, they might help a low resource pair to acquire extra knowledge from the other languages. Let's see, high resource language pairs, if you train it together with the low resource language pairs, they can be helpful to improve the performance of low resource language pairs. That's one motivation. And another motivation of MLMT is that MLMT systems tend to generalize better due to the exposure to diverse languages, right? It can lead to improved translation quality compared to bilingual MLMT systems. Then how about the goal? I think the goal of MLMT also contains 2 points. First, it's about have a one model for all language solution to machine translation, and maybe other NLP applications as well. And the second goal is that we hope that MLMT, because it learns shared multilingual distributed representations, so it can help machine translation or other NLP applications for low resource languages. Okay, that's a goal of MLMT. As I have mentioned, MLMT research is a very active research field. And here I tried to draw a very simple timeline about how MLMT research makes a progress until now. So if you are a NLP researcher or a machine translation researcher, you know that the MLMT research or MLMT boom starts from 2014, right? At that time, we had the first sequence-to-sequence model, which has been affected the foreign research, not only in MLMT, but also in NLP in general, I think. So in that year, 2014, we had the first MLMT model, and in 2015, we had the MLMT model with attention, which helps to solve the sequence to solve the generation of long sentences, right? And actually, just after the success of MLMT with attention, researchers have started the research on MLMT from 2016, which includes Multiway MLMT, multi-source MLMT, and raw resource MLMT. I'm not going to go into detail about what these three different MLMT scenario or user case mean, because we are going to cover it through this entire tutorial. But keep in mind that these three user cases based MLMT studies came after just the success of the MLMT with attention model. They appear in 2016. And after that, Google released its MLMT model, MLMT system, which has a very big impact. And in the same year, Google also released the transformer model. So before that, the MLMT model is based on recurrent neural network, right? And in the same year, in 2017, they released the transformer model. And from then, all MLMT studies or sequence-to-sequence or generating tasks are usually based on the transformer structure. And in 2018, we had the BERT model, the pre-trained language model based on transformers, which has a very big impact to the NLP research. And in 2019, let's go back to the MLMT research. We have a very interesting study on massive MLMT, which is an MLMT system studied on more than 100 language pairs. And in 2020, this year, Facebook released a very interesting research topic about a massive MLMT system. But that system is beyond English-centric. That you see, this in 2019, the massive MLMT system released by Google, this is again English-centric. But here, it's beyond English-centric. That means it is the system for any language pairs, even if without English. So it has been making very interesting progress until now, and we're also very looking forward to what will happen from now on. So for next, I will take a very brief look at what this progress look like. So first is about Google's MLMT system published in 2017. So in their system, they show that a single multilingual model can achieve comparable performance for English, French, and even performance better than a bilingual model for the English-German language pair on the WMT benchmark. And here shows the results of their paper. So we can see that there are several language pairs, the German English, French English, and also the one with some oversampling methods, and also Japanese English, Korean English, and Spanish, Portuguese, right? And this column shows the single means a bilingual model, and this column is a multilingual model. Multilingual model combines, for example here, combines German, English, French, English into a single model. And we can see that the diff means improvement from single model by this multilingual model. And the same thing happens on the language pairs of Japanese English, Korean English, or Spanish English and Portuguese English. This is the direction from other language to English, right? And this table shows the another direction, so from English to many other languages. Here the multilingual system does not show very consistent improvement, but again, in some language pairs, it can be helpful. Even the target language is not English, such as here English-German has been improved, and English-Japanese slight improvements, English-Portuguese slight improvements. And what's further being shown in that paper is that after they trained a MLMT system, they did a very interesting analysis. They showed that what their system have learned is actually they learned some language clusters. And here shows the language clusters clustered. And if we took a detailed look at what is happening, like here, so it's showing something like that. This is again not very clear. So let's have a look at the figure C here. So we can see that the English sentence, Korean sentence, and Japanese sentences, these three sentences are parallel sentences. And these three sentences has been classed together. What does it mean? So it actually is learning language independent semantics. So parallel sentences have been clustered together, right? So that's what the multilingual MT system has learned. And they also did another very interesting experiment called the mixing target languages. And here they did a linear corporation to weight the embeddings of the Korean and Japanese language. And we can see that when we set this WKO, the weight to some parameters like 0.58, and actually this is the source language is English and is trying to translate into either Japanese or Korean. And when we set this parameter in the middle, we can see that the output is a mix of Japanese and Korean languages. So this is also a very interesting finding from their paper. Next paper I want to introduce is Google's massive MLMT system. And in this paper, they studied more than 100 languages, and but still centered on English. And here shows the bilingual system performance from English to other language, and from any other language to English. And here the left side has more paracorpus, and the right side has less paracorpus. And the y-axis is Bruce scores. And we can see that this is natural, right? Because usually for language pairs that have more paracorpus, the Bruce scores, the translation performance will be better. So it's something like that. And on the opposite side, we also can see this trend. So this is about the bilingual system due to the paracorpus the imbalance problem, right? And in this paper, the authors tried to study a single massively MLMT model that can handle 103 languages, trained on over 25 billion parallel sentences. So how good are this massive system? So here shows an example of their system. We can see that now what happening here is that this black line is the bilingual baseline, is the bilingual baseline. And here is showing the translation difference comparing the bilingual system against the multilingual systems. And it has two versions of multilingual system. One is with oversampling, another is without oversampling. And with oversampling one is showing in green dots or green line. And we can see that with oversampling, it's better than without oversampling on both sides, right? Even here is any to English direction. And another finding is that on this area is for the language pairs that have a high resource paracorpus, and this area is an area that has a raw resource. So for English to any, we can see that multilingual systems are helpful for the very raw resource language pairs if we do oversampling. And if we look at this one, this is any to English. So from other language to English, for the raw resource, if we do oversampling, it extremely improves, right? For the most raw resource one, it can improve more than around 10 group points. So this is a very big improvement. So the observation from this experiment that the massive MLMT is helpful for raw resource languages, but not high resource languages. And they also did an interesting experiment to show the effect of the task numbers. So here task means language numbers. And again, they had a black line on the center of the figure, which is the bilingual baseline. And they compared using 10 languages to English, 25 languages to English, 50 languages to English, and 102 languages to English. And we can see that by adding more languages, it's unnecessary to improve the performance, right? Actually, here 10 languages shows the best performance. And although for raw resource, for the higher resource settings, they are not helpful, and for the lower settings, they are more helpful. And on the English to any translation direction, the trend is similar, right? So on the 10 language setting, it performs better compared to adding more language pairs into the multilingual system. So this observation tells that increasing numbers of languages are not always helpful. So that's two systems from Google. And when we go into this year, 2020, Facebook also released a very interesting system. That's an MLMT system beyond English-centric. What does this mean? So they released a system called M2M100, which is the first MLMT system that can translate between any pair of 100 languages without relying on English data. So this is, again, a very big progress, right? So before that, the Google's multilingual systems is still centered on English. Now, Facebook system can translate between language pairs without relying on English data. And they further show that their system, the M2M100, can outperform English-centric systems by 10 group points evaluated by Brew. And this is really a lot of training. You see, the M2M100 system is trained on a total of 2,200 language directions. And also, they show that this is 10 times more than previous best English-centric multilingual models. And here shows a performance table taken from their paper. We can see that they compare different models from the bilingual model, so biotext bilingual model, and the English-centric one, and their models, which is M2M100. We can see that they experiment on two scenarios, supervised and zero-shot. On all the scenarios, whether it's low resource, middle resource, or high resource, all zero-shot, the M2 M100 system outperforms the English-centric ones. This is, again, amazing. So MLMT system has been made a lot of progress, a lot of convincing progress until now. And so the goal of this tutorial is to present the basics of MLMT system to help you understand these. And we're also going to cover an in-depth survey of existing literature on MLMT, which is centered on use case, resource manuals, underwriting model principles, core issues and challenges of various approaches. We're also going to discuss the strengths and weaknesses of several techniques by comparing them with each other. Finally, we hope that our tutorial can inspire new ideas for both researchers and engineers who are interested in MLMT. So for now on, I'm going to first give a very basic introduction about MLMT. But before that, we must have a look at how MLMT works, right? So this figure shows the basic MLMT structure. So this is, we have the encoder and we have the decoder, and they are connected by attention. The encoder reads all the words and then convert it into a single representation, and the decoder, together with the attention mechanism, decodes the source sentence into target sentence word by word, so one by one, until we get the end of sentence. So this is the basic structure of MLMT. And as I have mentioned, there are two MLMT mechanisms. One is a recurrent neural network based one. So here we usually use LSTM recurrent neural network to connect all the hidden states from left to right. And we have an attention mechanism. So during decoding, the attention mechanism looks at how much we have to pay attention to each hidden state of the encoder, and then do decoder. And the decoder is, again, a recurrent neural network, such as LSTM. And now the main MLMT architecture is a transformer. So the difference between transformer and ARM-based ones is that, so before that, we only have this cross attention, so which is attention from decoder looking at the encoder side. But when we go to transformer also has a self-attention layer represented like this multi-head attention. So it do attention on both the source, both the encoder, both the decoder, and also do cross attention. And the encoder is consists of the multi-head attention with feed-forward layers. And move from MLMT to MLMT, I'm going to talk about two initial MLMT ideas. The first one is from Farland, 2016. This model is the first MLMT model, which is based on, of course, the encoder, decoder, and with attention MLMT architecture. But in their model, we can see that for each language, it has an independent encoder and also independent decoder. For example, for English, we have encoder 1, and for Hindi, we have encoder X. And these encoders, they do not share their parameters at all. And also for decoder, same thing. The only parameters being shared is attention. So their model tries to minimize the parameter sharing, only share the attention mechanism. And another initial MLMT model is the one proposed by Google. So their MLMT system. The difference between the previous one is that they propose a complete parameter sharing mechanism. That's saying both encoder and decoder and the attention mechanism, they are shared for all the language pairs. And the multilingual language pairs, they are combined together and trained with a single structure. That's another initial MLMT model. But today we're going to cover all other MLMT systems or models. So here shows an overview of MLMT taken from our survey paper, and we divided MLMT into 3 main categories based on their user case. The first one is Multiway modeling. So we have a Multiway corpus and how to do MLMT learning. And the second category is raw resource. And the last one is multi-source. And in Multiway modeling, we are going to talk about 3 core issues: how to do parameter sharing, how to deal with language divergence, and how to train them. And in the raw resource training, we are going to talk about the transfer learning thing, zero-shot modeling, and zero-resource modeling. Okay, so from now on, I'm going to give the mic to my colleague Raj and let him explain Multiway modeling for you guys.
Hello everybody, my name is Raj Dabre and I'm a researcher at NICT Japan. Before NICT, I was in Kyoto University working on my PhD, and before that I was in IIT Bombay working on my master's degree. I have mostly worked on multilingual machine translation, and for a while I also worked on morphological analysis and part-of-speech tagging. Recently, I've been focusing on efficient deep learning, where I focus on compact, flexible, and fast neural machine translation models. I'm going to mainly talk about topics related to parameter sharing, massively multilingual modeling, language divergence, and training protocols. So let's get started with parameter sharing. Firstly, my colleague has already established the foundations of multilingual neural machine translation by talking about a minimally shared and completely shared machine translation model. Now, these two architectures are not necessarily the best, and there has to be an optimal amount of sharing that can be done. And what we can do is empirically determine the amount of component sharing in order to find the right balance. So the questions we are going to ask are, how do we maximize the impact of shared vocabulary? How do universal encoders or decoders matter? Should attention be universal or language specific? And finally ask the question, how much sharing is good sharing? We are also going to talk about parameterized parameters for shared modeling, where we are going to learn about parameter sharing. So, no discussion can begin unless you talk about vocabularies. In a minimally shared model, the question of vocabulary sharing does not arise. But in a fully shared model or a partially shared model, there might be vocabulary sharing. The naive solution is to use a single vocabulary for all languages without any kind of discrimination or special handling, as done by Johnson et al. But in order to optimize the performance for partially shared or fully shared models, we might have to add some constraints. We found a paper by Wang et al. In ICLR 2019 on soft decoupled encoding. If you look at the figure below, you can see that instead of working on fixed subwords, they work on bag of character n-grams, for which, given a word, they extract all possible n-grams, then convert them into lexical embeddings and add them. Thereafter, they apply a language-specific transformation and a semantic transformation. They combine the language-specific transformation and the semantic transformation to obtain a word vector. This word vector is not only aware of the lexical properties of a particular word and the language, but also the semantic properties of that word. This word vector, being better informed, can be used in the encoder, and in their experiments they found out that this kind of word vector generation is very useful in transfer learning setups where a resource poor language can be helped by a resource rich language. Now the question is that will this technique work for a wide variety of Indic languages, because Indic languages are very much related to each other. Also, it would be interesting to do these experiments for groups of language families, especially in massively multilingual NMT settings, which I'm going to talk about soon. We found some recent papers by Chung et al. And Yu et al. in MLMT, and we encourage you to look up these papers and read for better understanding. Next, Wang et al. Also explored language-sensitive embeddings, where they augment shared embeddings with language-specific indicators or factors. If you look at the figure below, you have the word I and the embedding for that word I. But if this word is shared among multiple languages, then the embedding might not contain enough of distinguishing information. So you can use the language indicator, in this case en, and generate an embedding out of it. This embedding can be used to augment the word embedding either via concatenation or by addition. And then this can be fed to the encoder or the decoder as applicable. And this way of generating language sensitive embeddings should help in adding some additional knowledge to the existing word embedding. Now, what's important is that these language indicator embedding can be one-hot, learnable, or direction specific. Furthermore, we can also have language family specific shared embeddings, where we can have separate shared embeddings for different families. This way we can avoid any accidental n-gram vocabulary overlaps. Next, we are going to talk about sharing in encoders and decoders. Most works have agreed thus far on a universal encoder, such as works by Dong et al., Sachan et al., and Wang et al. And the reason for a universal encoder working good enough is because an encoder does not have any cross-lingual component, such as a cross-lingual attention mechanism. On the other hand, component sharing in decoders is tricky because finding the right balance between universal and distinct representations is the main challenge. Furthermore, the decoder consists of a cross-lingual attention mechanism, which means an attention mechanism between the encoder and the decoder, and this adds to the challenge. I want to focus on a work by Sachan et al. In 2018, who did an empirical study of what components in the decoder can be shared in order to get the best possible translation quality. So if you look at the figure below, for English to multiple target translation, there is of course a shared encoder for English regardless of the number of target languages. On the decoder side, there are a number of components that can be shared, such as the embedding layer, the attention layers, and the feed-forward layers, and finally the linear layer before the softmax. They empirically determined that having shared attention and embedding components but distinct feed-forward components are optimal for the best possible translation quality. In particular, having distinct feed-forward parameters help in language-specific adaptation. Their model is 20 to 30% smaller than a minimally shared model, and it furthermore improves the translation quality slightly. On the other hand, Wang et al. Focus on language sensitization. Before talking about language sensitization, they simplified the architecture by encouraging strong sharing between the encoder and the decoder. So between the encoder and the decoder, the self-attention and the feed-forward layers are common. So they use the same components in the encoder and the decoder. The only non-shareable component is the cross-attention mechanism. So this particular combination of the encoder and decoder results in a module known as the representer. This representer method was also used by Dabre et al. In their work on recurrently stacked neural machine translation models. Next, in order to make the encoders and decoders language sensitive, they used language sensitive embeddings. Language sensitive embeddings can be used by the previous factored based approach that I had mentioned in the previous few slides ago. You can also have language pair specific cross attention. If you look at the dotted component in the diagram, you will see that a different cross attention mechanism is used for a particular language pair. Finally, there is also a language discrimination, which means by taking the output of the representer, you can pass it through a discriminator which will predict the language to which that particular representation belongs to. By doing all of these three things, they found out that there is a general improvement of 1 to 2 blue. So what this means is either you can follow Sachan et al. And determine empirically which is the best amount of, what is the optimal amount of sharing, or what you could do is have some kind of language sensitization in order to make the model more aware of shared as well as distinct properties for different languages. Now that we're talking about language specific or language pair specific attention, it's important to talk about attention sharing. So now there is a universal shared attention mechanism proposed by Firat et al. Which puts too much load on a single set of parameters because there are multiple encoders and decoders which share a single attention mechanism. Next, there is a source specific attention mechanism which can reduce the load, but it's not known to be effective as shown by the work by Blackwood et al. In 2018. There is target specific attention. It apparently works the best according to Blackwood et al. And some other researchers, and it shows the importance of unshared components in decoders, especially regarding the cross attention components. And finally, you can have source target specific attention, which is what some of the researchers have explored, but despite having the least load on computation or the least load on coupling encoders and decoders, this particular source target specific attention mechanism can prevent zero shot translation. So far we have fixed the number of components that should be shared and unshared. But what if there were a way where you can let the model decide for itself what parameters should be shared and what parameters should not be shared? So in other words, if there were a mechanism which could automatically generate parameters for the encoder and decoder, then there could be a mechanism to loosely share or unshare parameters. So in Platana et al. In their work on 2018 on contextual parameter-based multilingual neural machine translation, what they did is they have an encoder and a decoder which have their own LSTM weights or self-attention or feed-forward components. But instead of updating weights for the encoders and decoder components, they instead have a parameter generator component. This parameter generator component is primed using the language embeddings. So if you look in the figure, the example is for English to Vietnamese. You have English embeddings, you have Vietnamese embeddings corresponding to the language tokens. And then these, once fed to the parameter generator, will generate parameters for the encoder and decoder. And then the encoder and decoder can perform the computation. During learning, the encoder and decoder parameters are updated, but this actually results in the parameter generator parameters being updated. So what we are essentially doing is generate parameters using parameters. And this parameter generator can generate parameters for the encoder and decoder independently using a decoupled parameter generation mechanism, or simultaneously using a coupled parameter generation mechanism. For the coupled mechanism, all you have to do is combine the embeddings of the source language and target language indicators. So parameters generating parameters is also known as a way to do metaparameterization. You can support parameter groups where you can have a parameter generator for specific language families. There is a related work on family specific sharing by Liu et al. And I encourage you to look it up. The advantage of contextual parameter generation is that compared to separate models or minimally shared models, this model can save a significant number of parameters. And furthermore, it can lead to a significant improvement in translation quality as well. They did an analysis by comparing the language indicator embeddings in order to determine language similarity. And something interesting shows up. Of course, we know that Italian is similar to Romanian. But this kind of embedding comparison shows that Vietnamese is similar to French. Maybe in the experimental setup that they had, Vietnamese benefited most from French because its embeddings and its representations were most similar to French. Now, the outcome of this particular analysis is we can have a two-step meta-learning, where in the first step, we group languages indiscriminately, discover groups, and then after that, separate languages into groups and then have group-specific multilingual neural models. Now that we are generating parameters conditionally, depending on the source and target language or both, we can also talk about conditional computation and neural architecture search. Neural architecture search is its own discussion, and that is not the focus of this particular tutorial. On the other hand, I'll be talking about tensor routing by Zaremoubi et al. 2018. What is tensor routing? Zaremoubi et al. In 2018 proposed an augmented encoder block. The encoder block is shown in the figure on the left-hand side. It takes in input as a word and the hidden state and generates the next hidden state. There are shared as well as unshared components, where the shared component is indicated by solid blocks and unshared components as the dotted blocks. These unshared components are specific to the languages. Now, shared components can have a huge amount of load on them, and therefore it's better to have multiple shared components. There is a routing mechanism which will take the content of the inputs and determine which block should compute which computation. Therefore, by routing vectors or by routing information to specific blocks, you can reduce the load on an individual block, and each block might be able to specialize in learning a specific aspect of language translation. And then finally, you can combine the outputs of all of the blocks to get a very high quality representation. So you have to also understand that each block can act as an expert, and this is related to works on mixture of experts and G-shard. I'll be talking about G-shard in the upcoming slides on massively multilingual machine translation. Up until now, I've talked about parameter sharing, where the purpose was to discover or determine an optimally shared architecture in order to improve the quality of multilingual machine translation models without having any kind of negative impact on the translation quality. Next, it's time to talk about massively multilingual models, where we crank up the number of language pairs in a translation model up to the maximum possible limit and determine how feasible it is to have a single model for all languages. In massively multilingual models, I'll mostly be talking about Google's work on MLMT in the wild, adapter layers, G-shard. I'll also be talking about University of Edinburgh's work on publicly available Opus data, and this work should be interesting to academics because it's done on publicly available data and hence is very reproducible. Thereafter, I'll be talking about the bottlenecks, where I talk about the hardware, computational and cost-related bottlenecks, as well as representational bottlenecks because of lack of parameters or lack of computational complexity thereof. Now, note that this work on massively multilingual models is rather recent, having started in 2019. Aroni et al. In 2019 trained the first massively multilingual neural machine translation model on 59 low-resource language pairs using a 6-layer transformer base. They saw that one-to-many models were better than many-to-many models for non-English targets, where they saw a 2 to 3 blue improvement over the many-to-many models. The reason for that was the relative overrepresentation of English, because in many-to-many models, there were English on the source side as well as on the target side. On the other hand, many-to-one models were worse than many-to-many models for English targets because of the relative underrepresentation of English. In other words, many-to-many models are better for translation into English, but not as good for translation out of English. Next, they pushed this particular model to its limit by incorporating 103 languages with a 6-layer variation of the transformer base. In other words, more attention hex and bigger hidden sizes and feed-forward layer sizes. They saw that many-to-one and one-to-many models are both better than many-to-many in this particular case, because the many-to-many model is overburdened with the sheer number of language directions. And the other reason that they observed was that the 103 lingual model, which was trained on a large collection of parallel corpora, indirectly contained n-way corpora, which is detrimental to the many-to-one performance. They saw that supervised NMT quality degrades with more languages, and zero-shot NMT quality increases with more languages. If you look at the table on the bottom left side, you can see the translation quality for many-to-one, many-to-many, and baseline models for three low-resource languages and a resource-rich language, and the target of this translation is English. You can see that for low-resource languages, as I've said before, many-to-one models are better than many-to-many models. On the other hand, for the resource-rich languages, the many-to-many model is better than the many-to-one model. With regards to zero-shot translation, you can see the graph on the bottom right side, which talks about Ukrainian to Russian zero-shot translation, and it shows how translation quality improves over the number of updates for different many-to-many models. So for 5-to-5 multilingual model, there is a certain amount of zero-shot translation quality, because this particular model was not trained on a direct Ukrainian to Russian parallel corpus. But as you increase the number of languages in the multilingual model, you can see that the zero-shot translation quality shoots up by a substantial amount, peaking at, and the quality peaks at a 50-to-50 model. Next, there was an extension of Aroni's work where the main focus was on pushing the limits of translation quality when using private data which is order of magnitudes larger than the publicly available data. So the starting point is that quality is directly proportional to the data size. If you look at the chart if you look at the graph on the bottom left side, the dots and the lines, they show what are the translation qualities for high resource languages to low resource languages from left to right respectively. So you can see that high resource languages generally have a high blue score and low resource languages have generally a low blue score. Their work focused on three main points. One, how to do optimal sampling in order to study the transfer interference balance. I'll be talking about this aspect a little bit later. The second focus was pushing the number of supported languages to the limit, and finally to see whether increasing the number of parameters to beyond 1 billion parameters has any positive or negative impact on the multilingual neural machine translation quality. So the experiment on having more languages and more directions had a very interesting outcome. So on the right hand side, there are plots of English to any and any to English translation for high resource languages on the left side to low resource languages on the right side. And it can be seen that regardless of English to any or any to English translation, no matter how many languages you have in a particular model, high resource translation more or less suffers. And low resource translation more or less shows a positive improvement in translation quality. Especially any to English low resource translation is extremely high when you have more and more languages in the system. The reason for that is that because when you have any to English models with a large number of languages, the number of English sentences on the target side dramatically increases. However, their experiments revealed that in general, having a 25 lingual model should be optimal, because the more number of language pairs you involve, the more complex the model is, and therefore it is unable to handle the overload of the number of tasks. And it is also better to have one-to-all and all-to-one models. All-to-all models in general degrade the translation quality, and you can see that in the tables below. Next, the question on whether larger models are helpful or not. There were experiments on 400 million parameters with transformer big and 1.3 billion parameters using two variations, either using the transformer deep model or the transformer wide model. The deep model had 24 layers with relatively narrower hidden filter sizes, and the wide model had 12 layers with very wide hidden filter sizes and more attention heads. If you look at the plots on the right hand side, once again, the performance for low resource to high resource languages organized from left to right shows that in general, transformer deep models favor low resource translation quality, whereas transformer wide models favor high resource translation. These experiments were mostly conducted on 128 TPUs with 4 million tokens per batch. Now, this is computationally expensive and it's not something most academics can do. Keep this in mind because I'll be revisiting this particular aspect soon. The next work I would like to talk about is Zhang et al., where they did this same kind of massively multilingual experiment on the Opus 100 dataset with 55 million sentence pairs. They focused on using deep transformers with depth-scaled initialization and merged attention mechanism, and they saw that it's better to have 12 layers than 6 layers using these two mechanisms for an improvement of up to 2 blue points. They focused on the expressibility scalability trade-off, where they saw that having target language specific normalization and language aware linear transformations between the encoder decoder helps improve translation quality by another 2 to 3 blue points. Finally, their focus on zero-shot translation showed that random online back translation boosts the zero-shot quality by up to 10 blue. By random online back translation, it means that randomly during training, you perform back translation in the zero-shot directions and then use it to train the particular model. This makes the model aware of the zero-shot directions and therefore boosts zero-shot translation quality. For my colleague will talk about zero-shot translation much later. So if you have any questions regarding these kinds of aspects of zero-shot translation, please ask him. Of course, you can ask me as well. One thing is clear. Training massively multilingual models is a very time-consuming task because of the sheer volume of data and the sizes of the models, along with the number of language pairs involved. Furthermore, it is also obvious from the previous slides that having language-specific transformations has a positive impact on the translation quality in the multilingual setup. So, wouldn't it be nice if we could use a previously trained massively multilingual model and then do something to it so as to focus on improving the translation quality for language pairs that exhibit low translation quality? Bapna et al. Did exactly that, where they introduced adapters on top of the encoder and decoders. So adapters are small feed-forward layers that focus on a specific language or specific language pairs. So what they did is, for the language pairs that they're interested in, they introduce small feed-forward layers and place these layers on top of the encoder and the decoder components. So what happens is, during training, you freeze most of the model and only train the adapter layer for that particular language pair using some new parallel corpus or the previously existing parallel corpus. By doing so, Bapna et al. Showed that you get 13.5% larger models, but the high resource pair translation quality is significantly improved. Why is this important? Because in multilingual models, high resource translation quality usually tends to suffer. The plot on the bottom right shows how translation qualities are impacted by adapter layers. The red line shows that a multilingual model without any adapter layers has poor performance for high resource languages compared to bilingual baselines. But by using adapter layers, the translation quality for these high resource pairs is significantly closer to the bilingual baselines. This means where previous multilingual models showed poor performance for high resource pairs, using adapter layers, we are able to improve the translation quality and still retain the bilingual performance. On the other hand, low resource languages showed more or less the same amount of translation quality compared to the multilingual models, and which is significantly better than the translation quality of the bilingual baselines. The questions to be answered over here are, what if we use multiple adapters for the same language pair? Is it possible to have a dynamic adapter size? And what is the optimal adapter base to model ratio in a massively multilingual situation? Now, adapters are essentially like experts, and previous work on mixtures of experts have shown that mixtures of experts significantly improve multilingual machine translation quality. So, Lepkin et al. In their work on G-Shard pushed the idea of mixtures of experts to its limit. They kept the multilingual neural machine translation architecture as a fully shared architecture with one small change. They replaced the multi-head attention with a multi-head attention followed by a mixture of experts layer followed by another multi-head attention. They also propose to halve the number of layers, thereby focusing on shallower layers, but by increasing the effective width via mixtures of experts. Now note that the more number of experts you have, the bigger your model becomes. And a bigger model cannot fit on a single device. So this is where engineering comes into play, where the experts are scattered over a large number of devices and some amount of sharding and model and tensor routing and combination is used in order to train this particular multilingual model. If you look at the results, first look at the table and the bottommost row. It shows a massively multilingual model with 96 layers. It takes a significant amount of time to train, and it gives a particular translation quality, average to be around 36.9 over all translation directions. It is clear that using mixtures of experts with significantly fewer layers, like 12 layers or 36 layers, has a very strong impact on translation quality, and it is able to beat this extremely deep multilingual model by a substantial amount. If you look at the best possible model, which is in row number 1, it uses 2048 experts scattered over 2048 devices and has 36 layers. And you can get an improvement of 7 blue globally over the deepest possible model, which does not use any kind of mixture of experts. So what does this mean? It means that we do not need to actually go very deep when we have to train a multilingual model. Instead, some shallower models with wider layers, especially wider layers simulated using mixtures of experts, should be good enough in improving the translation quality for individual language pairs in a multilingual setup. Now let's talk about some bottlenecks. Massively multilingual training needs some heavy hardware, which translates to requiring a lot of money, which means these kind of experiments can typically be done in industrial setups. Next, most existing work has been done by Google with TPUs. TPUs are faster than GPUs, and it is typical to use hundreds of TPUs for these experiments. Furthermore, if someone outside the industry wants to do this work, we don't know what the equivalent GPU setting is. And especially the most sad part about this particular type of research is that it may not be possible to do this very effectively in a university setting where the computational resources are rather scarce. Next, more devices and more data means more training time, which again increases the amount of money you need in order to do this kind of research. However, are the blue gains worth the mammoth models? Next, do blue gains also translate into human evaluation gains? And the most important question is, how do we even deploy these models? Because a G-shard model has more than 600 billion parameters. How do we deploy this? Do we use a single 2048 TPU cluster? We don't even know how costly this is going to be. Furthermore, we don't know how we can have continual learning on these models. In the future, it would be better to focus on language awareness and awareness of language divergence to have better neural modeling, because we are already clear on one thing, that model size, that is representational capacity, is no longer the bottleneck. Having talked about parameter sharing in massively multilingual models, it's time to dive a bit deeper and talk about differences between languages and how languages may interfere with each other and thereby prevent the improvement in translation quality, and solutions on how we can overcome the language divergence issues in order to push the quality of multilingual neural machine translation. On the topic of language divergence, I'll be talking about vocabularies and in particular sufficient and fair representation of languages via these vocabularies. I'll also be talking about lessons from visualization and language families, where we understand what is learned where. Finally, I'll also be talking about token-based control, where inputs are augmented with features. Before going any deeper, I'd like to point out that one important aspect of language divergence comes from the word order differences between languages. However, this is important when we talk about transfer learning, and therefore my colleague Anup Kunchkotan will address this particular aspect of divergence in detail later. With regards to vocabulary in multilingual neural machine translation, I think everybody can agree that a fair representation of vocabulary for all languages is very important to improving translation quality for all languages. Now, typically what happens is, if you want to train a multilingual neural machine translation model, all the corpora are combined and a vocabulary is learned from all the joint corpora. However, there is a skew in the data for different language pairs, and therefore there will be overrepresentation of some languages and underrepresentation of some other languages. To be more specific, we know that German is a resource-rich language, whereas Lao is a resource-poor language. So if we just combine the corpora for German and Lao, where Lao has smaller corpora, we know that the vocabulary for German will be much larger than the vocabulary for Lao, and therefore the representation in the multilingual model for German will be much better. There are some ways in which we can enhance the vocabulary for resource-poor languages. In particular, we can use large monolingual corpora. Additionally, we can oversample the vocabularies of the smaller corpora. But naively oversampling the vocabularies of smaller corpora and the languages associated with them will not be the best possible solution. There is a recent proposed work on temperature-based vocabulary sampling, where if P is the probability of sampling a particular vocabulary item for a language L, then we will change the probability of sampling by raising P to the power of 1 by I, where I is the sampling temperature. So that means if I equals to 1, then the vocabularies from resource-rich languages will be highly favored. And if I equals to a very high value, then vocabularies from the resource-poor languages will be favored almost as equally as the vocabularies from the resource-rich items. The other important aspect is to work on vocabulary sizes. Most works have shown that 32,000 to 128,000 subword vocabularies are optimal. We also need to study trade-offs such as sequence length, softmax computation time, and enough subwords to represent a particular language. There are some key observations in practice. If you look at the table on the bottom left side, it shows that larger vocabularies do not always bring proportionate improvements. Because larger vocabularies involve shorter sequences, they also have a negative aspect of having slower softmaxes. So it's important to do a cost-benefit analysis in order to determine what is the best vocabulary size setting. Next, previously I talked about some kind of temperature-based vocabulary sampling. There has been work by Bapna et al. And others where they showed that using some kind of moderate temperature sampling helps ensure fair representation for most languages. If you look at the table on the bottom right, it shows that if you use no temperature, if you do not use any high temperature for sampling, then you do get some reasonable translation quality for high, medium, and low resource translation. But when you use some reasonable temperature for sampling, then the translation quality for all sorts of high, middle, as well as low resource languages improve by a reasonable amount. Another aspect of divergence can be understood by the visualization of representations obtained from multilingual neural machine translation model. To the left is a figure which shows how multilingual neural machine translation models cluster languages into different language families based on the representations for the sentences belonging to those languages. So Kuduganta et al. In their work on SVCCA similarity between representations showed that multilingual neural machine translation models have the ability to discover language families. This was also observed by Johnson et al. And Dabre et al. What they observed is that encoder representations cluster sentences into language families. How do you obtain sentence representations? It's very simple. You take a sentence, you feed it to the encoder, and the output of the encoder can be averaged over all words in order to obtain the representation for a particular sentence. And the clustering seems to take place regardless of script sharing. In other words, if you have two related languages written in very different scripts, the encoder will still cluster them and show that their representations are very similar. Furthermore, if two languages which are related to each other and share scripts, their representations will be even closer. They also made an observation that high resource languages are the ones which cause the partition into different language families, and the low resource languages simply have their representations become similar to the high resource languages and belong to a particular language family. There is also evidence of representation invariance when fine-tuning is performed, which can explain poor zero-shot quality between distant pairs. Now that we know that multilingual models perform some kind of language family clustering, it's also interesting to study the representation similarity evolution depending on the depth. So the study shows that representation similarity varies with depth, where shallower layers tend to cluster languages according to script and deeper layers tend to cluster according to family. In other words, language families are more evident when you take representations from deeper layers of the encoder. A small case study of Turkic and Slavic languages, where Turkic languages such as Turkish, Uzbeki and Azerbaijani are written in Roman script, and Kyrgyz and Kazakh are written in Cyrillic script. If you look at the figure on the right side, it's very clear that the first layer of the encoder already is able to separate between Turkic and Slavic languages. But once you go deeper, it seems that the encoder manages to cluster languages belonging to a family even closer. So what this means is the first encoder layer separates by script and the last layer closes the gap. This helps distinguish between the Turkic and Slavic languages, where both these languages have Roman as well as Cyrillic scripts. Furthermore, a representation evolution study with respect to the depth shows that for many to English translations, the encoder representations converge and the decoder representation diverge. This can be seen in the two graphs above. For English to many translation, on the other hand, the encoder representations of English diverge based on the target language. So the question to ask over here is divergence a good thing? Does it cause a learning overhead? Should it cause a learning overhead? Because sometimes language divergence can increase the complexity of learning, which might be advantageous, and sometimes the increased complexity might affect learning and therefore reduce translation quality. So it's important to understand the right balance of language divergence in order to boost translation quality for all language pairs involved in the multilingual setup. Now that we know that multilingual neural machine translation models have the ability to group languages into specific language families, it might be a good idea to take an advantage of this particular behavior and learn certain language families and thereafter build language family specific neural machine translation models. Tan et al. Did exactly that. What they did was train a many-to-many model with language tokens, because language tokens can be used in a shared model to indicate the target language. Thereafter, with the embeddings learned for these language tokens, they did hierarchical clustering of tokens, where the number of clusters are set by elbow sampling. By setting the number of clusters, you essentially set the number of language families you are trying to learn. Now, if you look at the figure in the middle, you can see some predetermined language families according to linguistic knowledge. On the other hand, Tan et al. Empirically determined language families via their embedding clustering mechanism, and these language families are shown in the figure below, coded according to different colors. There is also work by Multiway et al. On a similar topic, and I encourage you to look it up as well. Once language families have been determined, Tan et al. Focused on determining whether empirical clustering helps or not. If you look at the upper table, then you see that language family specific clustering leads to better translation quality for languages. To be specific, if you look at the line labeled random, it means languages are clustered regardless of the language family they belong to. Family specific means using the predetermined language families according to linguistic information for language clustering. And of course, it has a strong positive impact on translation quality. But if you use the language families determined by embeddings, then you see that you can get the best possible translation quality, which means that you can use either predetermined language families or empirically determined language families to perform language clustering in multilingual neural machine translation. Next, you can also see that language family specific models are better than universal models. The table below shows that if you train a universal model involving all languages, then the translation quality is pretty bad for some languages. But if you use a embedding determined language family and then train machine translation models for language families, then you get very good translation quality for languages belonging to those language families. There are related observations by Dabre et al. So the next step should be to determine whether family-specific adapter layers on top of these family-specific models will be helpful in further improving translation quality or not. Furthermore, would it be nice to have a universal model where most of the components are shared but have family-specific vocabularies and certain components in the decoder being separated according to language families? And it would be very interesting to determine whether this kind of behavior will also be observed in extremely low resource settings or not. By extremely low resource settings, I'm talking about having fewer than 20,000 training sentence pairs. Now I'd like to talk about a rather unrelated but still important part of multilingual neural machine translation. In a fully shared multilingual neural machine translation model, we use a token such as 2xx to indicate the target language. Johnson et al. Showed that this is sufficient to prime the encoder so that the NMT model can generate a translation in the target language. The figure gives an example where you use the token 2JA to mark the English sentence to tell the NMT system to generate the translation into Japanese. Hai et al. Further experimented with distinguishing between shared vocabulary units, where what they did is not only did they prime the encoder with the target language information, but also with the source language information. What they did is they marked each source language token with the source language itself. Therefore, this prevents the encoder from being confused about words that belong to different languages. Blackwood et al. Further encouraged the use of language tokens at the beginning as well as the end of the source language sentence. Now, when we mark the source language tokens with certain language features, we can use a factored neural machine translation approach. By that I mean is that you can have the word I and get an embedding for that particular word, and then if you use en to indicate the source language as English, then you can get a feature for English. You can concatenate or add these two features and then feed it to the encoder. This augmented feature basically makes the encoder aware of the word as well as the source language to which it belongs. Ha et al. And Hokam et al. Said that it's important to keep word embeddings independent of task, which is the target language, via features. Now it's time to talk about training protocols. With regards to training protocols, I'm going to first talk about the MLMT training fundamentals, followed by training schedules, ways to leverage bilingual models, and ways to expand the capacity of models, and also about incremental learning. We already know how to train a neural machine translation model. What we do is, for a particular parallel corpus, we feed it to the model and then minimize the negative log likelihood for that particular language pair. In a multilingual setting, we simply feed parallel corpora for all language pairs and minimize the average of the negative log likelihood over all languages or all translation directions involved. The challenges here are finding a good training schedule and focusing on language equality. By training schedule, I mean how sentences from different language pairs are fed to the neural machine translation. So this depends on the type of neural machine translation model that we're trying to train. If we're trying to train a minimally shared neural machine translation model as proposed by Firat et al. Or Dong et al., then we would have to cycle through the parallel corpora for different languages. So if you have L1, L2, L3, L4, L5, L6 pairs, then you would first take a batch from L1, L2 pair, feed it to the model, then a batch from L3, L4, and so on and so forth. Now the problem is that this method has the risk of forgetting of language pair information in a previous batch. So suppose we are sampling a batch from the L5, L6 parallel corpus, then it's possible that whatever information we had learned from the batch from the L1, L2 corpus might be forgotten. This aspect is known as catastrophic forgetting, and it's not just a problem for multilingual neural machine translation, but also for machine translation in general. This can especially impact transfer learning setups. Now, if we have a fully shared multilingual neural machine translation model, then we don't need to worry about any kind of cycles. All we can do is simply mix all the corpora, shuffle them, and then choose batches from this shuffled and mixed corpus. Now, a single batch can contain sentence pairs belonging to multiple languages. But how do we address a situation where only parts of the models are shared and parts of the models are language specific? In this case, what we can do is have a batch which consists of sentences from multiple language pairs, and then shard it whenever you want to compute language specific components. So you would have a batch, say, consisting of sentence pairs belonging to 2 languages. Then just before the language specific component computation, you split the batch or shard it into 2 sub batches, feed it to the appropriate components, and then stitch the two batches together to get the original batch back. Along with the training schedule, it is also important to address language equality. Remember when I was talking about vocabulary, I mentioned that it is important to have fair representation for all languages. And therefore, while sampling vocabulary, it's important to sample vocabulary fairly across all languages. The same applies during training. So the source of inequality, as we already know, comes from the corpora size skews. In other words, for languages such as German, there are very large corpora, but for languages such as Lao or Vietnamese, there are very small corpora. There are solutions involving oversampling the smaller corpora. Before diving deeper about oversampling, the question is, should oversampling be performed before training or during training? Now that's a matter of implementation choice, because oversampling before training simply creates large duplicated corpora to be stored on text. This used to be done before, but these days some more clever approaches have come up. We already know that if we do not perform any kind of oversampling, then the model will focus on the high resource pairs while ignoring the low resource pairs simply because of the corpora size skews. On the other hand, if we simply oversample the smaller corpora to match the sizes of the larger corpora, then it might help improve the translation quality, but this kind of overwhelming oversampling will increase the amount of training time, and this might not be the optimal solution. So there is a new approach called as temperature-based sampling. This temperature-based sampling was already used for vocabulary sampling, and it can also be used for parallel corpus sampling during training. So if PL is the probability of sampling a sentence from a particular corpus, then temperature-based sampling is simply done by PL to the power of 1 by I, where I is the sampling temperature. If the temperature is 1, then high resource pairs are strongly favored. If T equals to 100, then low resource pairs and high resource pairs are equally favored. But if T equals to a value of 5, then low resource pairs are slightly oversampled and high resource pairs are slightly undersampled. If you look at the figures to the right side, then it shows what happens to English to any translation and any to English translation using multilingual models for high resource to low resource languages from left to right side. You can see that if you do not perform any kind of temperature-based oversampling, then low resource translation quality suffers significantly. But on the other hand, if you use high temperature sampling or some moderate temperature sampling, then low resource translation improves significantly and high resource translation is more or less the same as when no temperature was used for sampling. This means it's very important to give some kind of fair representation for low resource languages, especially in a massively multilingual setting, and temperature-based sampling is one of the good approaches to give some kind of fair representation. Now, we already know that training a model from scratch is very challenging, especially if you're trying to train a model on billions of lines of corpora on 103 different languages. Then the model has to deal with a lot. It has to deal with a very complex training procedure, and several languages may interfere with each other during the learning process. The solution is to leverage bilingual models or smaller multilingual models which are easier to train. The key principle is to use transfer learning via sequence level knowledge distillation. Kim et al. In 2016 proposed sequence distillation as a way to compress neural machine translation models. How does sequence knowledge distillation work? Simply put, you take an L1, L2 parallel corpus and train a large NMT model. You then decode the source language L1 sentences using beam search, greedy search, or ensembling to get an L1, L2 prime parallel corpus. This is known as the distillation data or the distillation parallel corpus. This distillation parallel corpus is a smooth version of the original parallel corpus. And therefore, if you train a small neural machine translation model on this distillation corpus, you can still more or less retain the translation quality of the large NMT model that was used to generate the distillation data. So how do we use this for multilingual neural machine translation training? Simply put, we take the parallel corpora for different language pairs, train large models, generate the distillation data, and then use these distillation data to train MLMT models. Given that the distillation data for all of these language pairs is rather simpler, they do not require an abundant number of parameters to be able to retain the high translation quality. So in other words, if you remember that in a multilingual neural machine translation model, high resource language pairs usually show reduced translation quality. Now, by using distillation data, we do not need complex models anymore to retain the translation quality of high resource pairs. And this type of a model, as showed by Tan et al., helps retain the best possible translation quality for high resource languages while improving translation quality for low resource languages as well. Now, it's time to talk about incremental training, where the objective is to expand the capacity of existing models with maximum reusability. The most promising approaches are by Surafel et al. And their work on vocabulary expansion, Escalano et al. With their work on gradual capacity expansion, and by Bapna et al. On their work on adapter layers. So we've already talked about the work on adapter layers, so I'll be focusing on the previous two works. Surafel et al. Proposed some simple methods to incorporate new languages into a multilingual neural machine translation setup. The left-hand side of the figure shows a simple way to have language-specific transfer. So you have some initial data for certain language pairs. You get some vocabulary from this initial data, have embeddings corresponding to the vocabulary, and an encoder-decoder model. When you have some new data coming in, it's possible that some of the old vocabulary may no longer be applicable, and some new vocabulary might be introduced. So all you have to do is replace the old vocabulary, introduce some new vocabulary, initialize the new vocabulary with some random embeddings, and then fine-tune on this new data. This method is similar to the transfer learning work done by Zoff et al. On the other hand, if you wanted to not only focus on this particular new data, then all you would do is expand the existing vocabulary with the new vocabulary items and random embeddings for these new vocabulary items, and then train on a combination of the previous as well as the new data. This method of fine-tuning a previously trained model on old plus new data is also known as mixed fine-tuning, proposed by Chu et al. 2017. This might increase the computational capacity, but is a very effective way for having additional language pairs and additional domain information in a multilingual setup. Another approach proposed by Escalano et al. Aims at capacity expansion of existing models, where the objective is to add new components while freezing existing components. So on the right hand side, you can see that there is an existing setup with one encoder and two decoder corresponding to language X and language Y respectively. No, that's wrong. Escalano et al. Proposed some techniques for capacity expansion of existing models. The idea is to add new components while freezing existing components. On the right hand side, you can see an encoder and two decoder setups, where on the source side you have language X, and on the target side you have language X and language Y. Suppose you add a new language Z, then all you have to do is take language Z, language X parallel corpus, freeze the entire model with the except of the encoder for the language Z, and then train the entire model. So that means only the parameters for the encoder corresponding to language Z will be updated. Now, because language X and language Y on the target side are already aligned, this might enable some kind of zero-shot translation for language Z to language Y. Now, the advantage of this method is that the training is a very lightweight method because you only update a very small set of parameters. But the disadvantage is that the previous components might not be aware of the new languages. So zero-shot learning might work, but not all the time. In their experiments, they've mostly focused on very closely related languages such as Spanish, French, German, and English. And it would be nice to see if this kind of zero-shot translation works for distant languages or not. We could additionally borrow lessons from Sachan et al. And Firat et al. And Bapna et al., where we can use some kind of adapter layers instead of adding whole new encoders. Furthermore, we can only update these kind of added parameters. Next, instead of simply adding a new encoder, it might be possible to deepen the encoder and allocate these deepened components for the new languages that are introduced. With regard to multilingual neural machine translation training, there are some correlated topics which have not been well addressed yet. In particular, the aspect of diverse language learning rates. We know that language pairs are learned at different rates. In other words, when we do multilingual neural machine translation training, we concatenate all the corpora and train till convergence on a particular metric. But this does not address the fact that certain language pairs have been already learned significantly and we do not need to iterate over the corpora for those particular language pairs. So Jean et al. Have addressed this partially by setting task weights using model performance. So in other words, once the model detects that the translation quality for a particular language pair has reached more or less to an optimal value, the weight for that particular language pair or that particular task is reduced so that sampling for that task will happen less frequently. This will prevent the machine translation model from overtly training on a particular language pair. We can additionally take lessons from Wang et al. 2018, where you can add or remove instances from the training set as required. Catastrophic forgetting is another important topic which needs to be addressed for multilingual neural machine translation. Thompson et al. Have already talked about catastrophic forgetting in the context of domain adaptation, and it may be worthwhile to explore this in the context of multilingual neural machine translation. There is also a problem with the way we detect convergence for multilingual neural machine translation models. Currently what we do is take the evaluation corpora or the development sets for all language pairs, concatenate it, and stop training when convergence on the evaluation metric is detected for the average performance over all pairs. This ignores the individual pair's performance and is unwise. Maybe it's time to consider some kind of a weighted performance metric which gives different weights to different languages depending on their learning rates. Furthermore, some kind of better evaluation metrics for MLMT settings might be needed. To summarize, Chu Cheng-Hui introduced multilingual neural machine translation and established the foundations of MLMT. After that, I spoke about multi-way modeling, where I focused on parameter sharing, massively multilingual neural machine translation, language divergence, and multilingual neural machine translation training. The reason why multilingual neural machine translation is interesting is because it strongly benefits low resource languages via transfer learning. Now my colleague Anup Kunjkutan will expand on this particular aspect on low resource translation.
So thank you, Raj, and welcome everyone. So after the previous section on multi-way modeling, let's move on to the next section of this tutorial, where we will go over an important aspect where multilingual NMT is useful, which is translation for low resource languages. So before we get started, let me just introduce myself. So I am Anup Kunjkutan, and I work as a senior applied researcher at Microsoft India with the machine translation group. Before that, I did my master's and PhD from IIT Bombay, and have worked at Persistent Systems on machine translation and NLP related problems for life sciences domains. My research interests are primarily in the area of multilingual NLP. Particularly, I am interested in machine translation and transliteration. I'm also interested in representation learning for NLP. A lot of the interest in multilingual NLP stems from my interest in Indian language NLP and in building resources and tools for Indian language NLP. In this part of the tutorial, we will sort of broadly divide it into two parts. In the first part, we will go over transfer learning for multilingual NMT for really low resource languages. And in the second part of this section, we will look at how do we translate between unseen language pairs using multilingual NMT. So let's get started with the first part. So as Chen Hui mentioned in the first part of the tutorial, that there is a very large skew in the parallel corpus availability across the languages of the world. A few languages are very high resource languages where we can build high quality translation systems given bilingual corpora. But then there are many languages, even in the top 100, 200 languages in the world, for which we have very limited amount of parallel corpus in a general domain across or spanning multiple domains. And then there is a really long tail of the thousands of odd languages in the world where really very little data is available. So how do we support translation for this long tail of low resource languages? It's very difficult to obtain parallel corpus for many of these languages. So the question is, can high resource languages help low resource languages in improving translation quality? Which means how do we build multilingual NMT systems where we can sort of transfer knowledge from high resource language pairs to low resource language pairs. And this brings us to the central point of this section, which is transfer learning. So transfer learning is a well-known technique in machine learning, where the general principle is how can you use knowledge gained in solving one problem to solve another difficult, different but related problem. And as applied to machine translation, what it means is this. So we have parallel corpus for a high resource language pair, say English French. We need to train a translation system for a low resource language pair, say English Galician. And for the high resource language pair, we can train a translation model. Let's call it the parent model. Now, what does this parent model capture? So it captures a lot of knowledge. It captures knowledge about concepts in the world. It captures domain knowledge if the translation system is for a particular domain. It captures knowledge about the languages involved in terms of the grammar. It captures knowledge about source to target transformation, the rules, representations of the internal network that have to be sort of applied in order to obtain the translation. So what we are looking to do during transfer learning is to sort of transfer this knowledge to what you would call a child model, which is a model for your language of interest, language pair of interest, and augment the knowledge that you can gain from the limited low resource small parallel corpus that you have for your language pair of interest. So that primarily you can look at this two transfer learning scenarios which people have tackled in the literature. So one is many-to-one translation, and the other is one-to-many translation. So many-to-one means that you are looking to translate to one particular language. The target language is fixed, whereas on the source side, say you want to translate from Galician to English, that's a child pair, but you also have access to, say, Spanish English. So Spanish is the high resource language pair, and on the source side you have the parent Spanish language. So that's the many-to-one scenario. The one-to-many scenario is the inverse of this scenario, where the source is fixed, and on the target side we have a parent and corresponding English to Galician, and English to Spanish is the high resource pair. A lot of work has gone to the many-to-one scenario, and a limited amount of work has gone into the one-to-many translation scenario. So we'll look through the literature in both these scenarios. So what we'll do is, in this section, we'll break this up into 4 topics. So we'll first go over the training methods used for transfer learning. Then we look at 2 important issues that transfer learning has to deal with. So when you're transferring knowledge from a parent to a child, we need to know if the vocabularies of 2 languages are different. How do we address this gap in vocabulary, which is what lexical transfer tries to address, and if the syntactic structure close this gap. Finally, we will look at what is the impact of language relatedness on transfer learning. So let's get started with the training methods. So the first training method is joint training. So we have looked at this in the previous section when training a single multilingual NMT model for a bunch of languages. In this way, when you train a translation system. So we are jointly training the high resource language pair denoted by P and the low resource language pair, the child language pair denoted by C. We may have to sample so as to balance the two corpora and then train a joint model. So in this case, we are not optimizing for the child language in particular, but we are training a joint model. But in the process, we also end up sharing network components and transferring knowledge from the high resource language pair to the low resource language pair. And what is seen is that in this case, there are many major gains in the many-to-one direction, but gains are limited in the one-to-many direction. The other setting that we look at for transfer learning is fine-tuning, and this is what we'll explore mainly through this section. So in this case, what we do is we start by first training a model for the high resource language, for the parent language pair. So this we can call this as pre-training, and we have a model for the parent language pair. Now, once we have this, we continue training the model, but now train it on the small amount of parallel corpus available for the child language pair. Okay, with this process is called fine tuning. At the end of this, we have a model that is tuned for the child language pair C. So if you compare fine tuning versus joint training, so fine tuning seems to be better according to some studies for the 1-to, and in the other direction, that is many to one, joint training seems to be better. Now, what you can do with fine tuning is that you can sort of specify a set of parameters to be tuned. So you don't have to always fine tune the entire network, all the parameters, but you can choose to freeze some parameters and tune the rest. And the thumb rule, what has been found in some studies, is that for the many to one direction scenario, it's good to sort of tune the encoder bottom layers, since these are the more language specific parts of the network, whereas for the one-to-many scenario, it's better to train to tune the decoder top layers while freezing the other parts of the network. So tuning a few parts of the network helps to avoid the scenario that the network forgets everything that it has seen from the parent language pair. Further, in some cases, the data for this child language pair is very small, and what can happen is that the fine-tuned model may overfit on this corpus. So to avoid that, you can sort of take a sample of the high resource language pair also, and after the initial pre-training, in fine-tuning, you sort of fine-tune on a mix of both the child language pair and the parent language pair in order to get a model tuned for the child language pair, but avoid overfitting. In these scenarios we saw so far, we were looking at transfer from multiple from a single parent, but we can also think of scenarios where you have multiple high resource parents available. Okay, in this case, what you can do is, just like you did a joint multilingual training, you can first do a pre-training to train a model on all the high resource language pairs jointly to get a single multilingual model, and then fine-tune on the language of interest. So rapid adaptation of a multilingual model for a new language pair in a very short period, say in times of natural disasters, etc., where we don't have the time to train a complete model from scratch. So you can take a representative set of high resource languages, pre-train a model, and then as needed, as limited amount of parallel corpus is collected for the low resource language pair, quickly tune the high resource, the pre-trained model for the low resource language. We can have a scenario where we have multiple children, right? What has been observed in the literature is that in the one-to-many scenario, transfer learning is not as helpful as the many-to-one scenario. However, sometimes when you have multiple child languages available where you want to transfer to all these languages. A good strategy that works well is to first pre-train on the parent language pair, of course, and then have a multi-stage tuning approach where you first tune jointly on the parent language plus all the child language pairs, so that you get a model that is tuned for all the child languages, and then you do a final fine-tuning step for the child language. So what this ensures is that in the second stage, the multilinguality sort of helps to improve translation on the final language pair of interest. In all the training scenarios that we saw, we were first pre-training the high resource language pair and then continuing to train and fine-tune for the language pair of interest. Now the question is, what is the objective of the parent model training or the pre-training? So the standard training that we do is the cross-entropy training, which tries to optimize performance on the parent tasks. Now, when we're trying to improve translation for the low resource language, is that what we need to optimize the parent tasks for? So that's probably not what we want to do. What we actually want to do is train the parent model in such a way that we optimize performance on the child tasks, as well as maybe enable few shot learning for the child tasks so that you can learn the child tasks with as little data as possible. Learning. So what we do here, so let's compare meta learning with other scenarios we have seen so far. So the standard transfer learning scenario is where we train a high resource language pair. So the parameters theta are sort of optimized for the high resource language pair, ES, Spanish in this case, and then from there we fine tune for our language of interest, say Romanian or Latvian. In the multilingual transfer scenario, we train a bunch of languages jointly, high resource languages jointly. So the parameters theta are optimized as an average to sort of give an average optimal performance on these high resource languages, and then from there we fine tune on the low resource languages. The idea behind meta learning is that we find out a set of parameters theta that are sort of such that starting from those parameters theta, we can quickly optimize for the language of interest. So we are not looking for optimal parameters for a language pair in particular, but for those parameters from where you can rapidly adapt to new language pairs. So that's meta learning. That's the idea for of learning to learn, which means you're trying to learn a model which can easily learn given new data for a new language pair. Okay. And so what we want to come up with is a scheme for initialization with only a few examples. So one particular framework for meta learning is model agnostic meta learning, and this has been applied to multilingual NMT for low resource translation. So let's see how that works briefly. So we have a bunch of language pairs that we want, which are the high resource languages. So we want in our meta model, so to say, so that it performs well on unseen language pairs, and we can do few shot learning. So what we do is we sample one of the language pairs and do a bunch of steps. So I'll illustrate the steps for every language pair, for a single language pair, and this has to be applied for every language pair. So we sample a language pair, we sample a few training examples for this language pair, we simulate a training step. So this means that we compute the cross entropy loss, compute the gradient. We do not update the parameters of the meta model. Instead, what we do is now select a few test examples. Now note that the test examples are different from the training examples. And we do this because in the meta learning scenario, we want to see how the model performs on unseen data. So using the updated parameters, theta I dash, we compute the error on the test examples. Okay, and so these errors are the errors generated by the adapted model parameters theta I dash for this language pairs. So similarly, we would have updated parameters for every language pair, and we would have errors for every language pair. Okay, but these parameters are not the meta model is not updated with these language parameters. Instead, the errors from each of the sort of simulated model updates are averaged, and then you compute what is called a metagradient. So the metagradient is that you compute the gradient with respect to the original model parameters theta, but on the loss incurred on the sort of simulated updated parameters theta I dash. So this sort of captures this scenario where you are trying to find out those set of parameters theta such that with just a few updates, because you took only one single update during the training step, so with a few updates, how can you get good performance on the child tasks. So with this, now we update the original model parameters, and then this process is repeated. Training setup, we only used the set of language. We used a fixed set of languages, but this also works well when we have a new language pair which has not been seen during training, and even in this scenario, meta learning works well, and it outperforms the multilingual fine tuning strategy on unseen pairs. Of course, this also requires far fewer adaptation steps for comparable performance. Next, let's look at how do we do lexical transfer, which is how do we bridge the gap between the vocabularies of the parent and the child languages. So what we have is that we have trained the parent model, and during the process the parent model's word embeddings or token embeddings have also been learned. The child vocabulary may be totally different. So how do we initialize the child's token embeddings? So one simple strategy is random assignment of child tokens to the parent language tokens, and this works fairly well. Better way to do this is if you have access to a bilingual dictionary between the parent and the child languages, then we can assign the parent's embeddings to the corresponding word in the child language. And in terms of performance, so the dictionary initialization is of course faster than the random assignment in terms of convergence, but eventually the random initialization or the random assignment also achieves comparable performance. However, when we use a bilingual dictionary, we are limited by the dictionary we have. So what we can also do is look at this literature on learning bilingual embeddings, wherein we start with monolingual embeddings for two languages and a seed bilingual dictionary, and we can learn a linear mapping function which can transform embeddings from one language to the embeddings in the other language. So if you have learned such a function, then what we can do is, once we have trained the parent model, we look at the parent model's embeddings and then learn a mapping function from the monolingual child embeddings to the model's parent word embeddings. With this, we can now transform the child's embeddings into the space of the parent, and then continue with fine tuning. An alternative to this is, of course, that we can map both the parent and the child into a common space. And this approach gives good improvements over random assignment of embeddings and is more generalizable, is not limited to the available bilingual dictionary. The second divergence that we need to take care of between the parent and the child is syntactic divergence. So suppose the parent and the child have different word orders. It's then conceivable that the contextual representations that are generated from the encoder in a many-to-one scenario are very different between the parent and the child. So alignment between the encoder representations is not very easy, and transfer is not very effective. So what do we do in such a scenario? So we don't. So one approach is to say that, okay, let's not over optimize the parent model for the parent word order, and to do this, we introduce noise in the parent source sentences while training the parent model. And this can be different kinds of noises that can be introduced in the parent source sentences. This could be word insertion, word deletion, word swapping, etc. Okay. This is a simple method and gives modest improvements over the baseline fine-tuning approach. Next, another approach is to say that, okay, what if we can do some pre-processing and reorder the words in the parent sentence to match the word order of the target of the child's sentence. Now, if we can do this, then we can ensure a better alignment between the encoder's contextual embeddings. So I'm talking about this in the setting of a many-to-one fine-tuning setup. So that's one approach that has been found to be very effective. So you reorder the source sentences of the parent, then train the parent model. Now the parent model's contextual embeddings have the same sort of properties as the child's contextual embeddings, and therefore when you fine-tune the child language there is a better alignment and you see a much better transfer. But this needs a parser or a system to learn the reordering between the source and the parent and the child languages. Finally, let's see how language relatedness is important for transfer learning. So far we have not discussed that, but when we started this discussion we said that transfer learning looks at scenarios where you're transferring between similar tasks. So let's see how that matters. So what do we mean by language relatedness? So languages can be related in different ways, but in this context what is important is a couple of ways in which languages are related. So one is languages could be related by genealogy. That means that they belong to the same language family. The languages have some sort of sibling relationships among them, and this results in language families. So we have language families like the Indo-European language family, Dravidian, Turkic, etc. Resulting from such relatedness. The other relatedness that is important is relatedness by contact, where languages in a certain geographical area have spoken by people have interacted over a long period of time, have exchanged vocabulary, grammatical features, and have achieved a level of convergence to the extent that they are recognized as what is in linguistic terms called a linguistic area. So a couple of examples of such linguistic areas were the Indo-Aryan, Dravidian language families, and a couple of other language families have interacted over a long standard average European across the European mainland is also considered to be a linguistic area. So when languages are related, they have some key similarities which are important to machine translation. So I've taken an example from Marathi and Hindi. So these are Indo-Aryan languages spoken in India, and but these similarities sort of fold across many other similar language pairs. So one is that there are lexical similarities, which means that there are words that are shared across these languages. These could be cognates and loanwords. Then there are morphological correspondences in terms of the suffix systems, case marking systems, postpositions of these languages. And finally, in many cases, related languages may also share the same basic word order. So if we look at our previous discussion where there was a lot of effort needed to achieve syntactic and lexical transfers, when it comes to related languages, the effort might be lower. Okay, and therefore, it is possible that related languages, when you're using related languages as parents to a child language, we may be able to achieve better transfer. And more evidence for this hypothesis comes from various languages from multilingual MLMT systems. So if you look at these these encoder representations at the top of the encoder stack, so where you expect the representations to be the most language independent, we see that they still cluster by language family, and not just by language family, but what is also interesting is that some sort of contact relationship is also captured. So for example, the Indo-Aryan and Dravidian clusters are sort of fused with each other, or the Baltic and the Slavic clusters, the Uralic and Baltic clusters are close to each other. So contact relatedness is also captured, and therefore languages which are related by such relationships are good for transfer. And some work, previous work in this area has also shown this to be true, that related languages do actually work as better parents than a random choice of a parent language for transfer learning for NMT. What is interesting is also that related languages which use different scripts also cluster together. For example, Hindi and Urdu, which are fairly the same language but written in very different scripts, also cluster together. So how do we use lexical similarity? So a straightforward way is to say that, okay, instead of training the word level, train our translation models at the subword level. So when we train at the subword level, we maximize overlap between the parent and the child vocabulary, and this encourages better transfer. And this work by Nguyen and Chiang show that when you use Uzbek English as a parent language parent, Turkish English and Uyghur languages, in both these cases we achieve a much better transfer when using subword level vocabulary compared to word level vocabulary. And if you look at the parent-child overlap also, the overlap is much higher when using a subword vocabulary. Now, what happens if the languages are related but use different scripts? So, even in these cases, transfer works well, as borne out by the encoder representations, but we may sort of further help the process if we can bring the representations, the surface representations of the two languages into the same character space, so that the embeddings are share the same vocabulary. So if the scripts are very similar, then it's very easy to map between the two scripts. So as an example, Slavic languages are such that some of them are written in the Cyrillic script, some in the Roman script, and the mapping between the two scripts to a large extent is very easy to do with rules, and so we can use a simple rule base to sort of get them into the same script, all the data into the same script. Similarly, many Indic languages use different scripts, but all of them derived from the same Brahmi script following the same principles, so it's easy to map, have one-to-one correspondence between most characters in these scripts. Okay, when the scripts are very different, then it's difficult to apply simple script conversion, but some sort of approximation can be done by using romanization, which means to represent these scripts in the Roman script. So romanization schemes have been defined for pretty much all the major scripts, and you can look at the Romanized version and train on the Romanized data, and hope that the resulting increased overlap in the subword vocabulary improves transfer learning. And it has been found that indeed, at least in the case of related languages, romanization does help. So even without script conversion, we do get benefits, but script conversion sort of provides further benefits. What I also want to emphasize is that transfer can also be done between languages which are related by contact. Say Hindi, which is an Indo-Aryan language, can serve as a good parent for Tamil, which is a Dravidian languages, but within the Indian subcontinent linguistic area. Finally, one more example of how language similarity can be used. So when we discussed that when we are fine tuning on a on a low resource language pair, we may run into overfitting. So one way to avoid it is to sort of do mixed fine tuning. Now, when you're doing mixed fine tuning, it is best if you use a language that is most similar to the language pair, the low resource language pair of interest, because they share a lot of characteristics, and hence that works out better. we can also use syntactic similarity between these languages. So going back to the previous example where we had to bridge the syntactic divergence between the parent source and the child source, and we needed to write reordering rules to convert the parent source word order to the child source. Now it may be expensive to write rules for every language, but if there are multiple child languages involved, say Indo-Aryan languages, now all of them have pretty much the same syntactic properties, the same word order. So if a single set of rules is written for English to Hindi, the same set of rules can be reused across most Indo-Aryan languages, and it has been shown that this works well. So you can use the same rule base. In fact, rules optimized for Hindi work well for most other Indo-Aryan as well as the broader languages in the Indian subcontinent. The last question we'll address is the question of parent data selection. So which examples in the parent language are most useful for transfer? Let's look at the scenario of many-to-one translation. So we have a sentence pair SIT for the parent sentence pair, and suppose we have S1 to S5. Now we can score each parent sentence by the probability that it belongs to the low resource language pair, or how similar, how likely is it to be a low resource language sentence also. Okay, and give more weight during training to those examples which are likely to be more compatible with the low resource language. So the scoring functions that can be used, a simple scoring function is sort of vocabulary overlap between the words in the sentence in the high resource language and the vocabulary of the low resource language, or it can just be how well a high resource language sentence scores in terms of the language modeling score on language model for the low resource language. And this notion can be extended to multiple parent languages also. So you can have multiple parent languages and you can score examples across all these languages using this scheme. You could also sort of come up with a language level similarity score. So instead of having similarities for every example, now we could see parent languages to the child language and then weight all the examples in a certain parent language in a certain way compared to examples in some other parent language. And this also gives benefits over just using all the parent language examples or examples from all parent languages uniformly. So with this, we will move to the next part where we look at an even more difficult scenario where we do not have any training data for a given language pair. So the scenario we are considering is this. We want to translate between language X and language Y. We do not have any parallel corpus between these two languages, but both languages share a parallel corpus with a bridge or a pivot language. Typically, English is one popular pivot language. So in this case, traditionally pivot translation is the method of choice, but with multilingual NMT, zero-shot translation, zero-resource translation has become possible. And all these methods are typically with a single bridge language, but recently there have also been approaches which look at multi-bridge approaches. We will also cover that. So let's start with what is pivot translation. So with pivot translation, what we do is we have independent translation systems between the source and the pivot language and between the pivot and target language. So suppose you want to translate between Hindi and Malayalam. You have translation models from Hindi to English and English to Malayalam. So we create a pipeline of these translations so that Hindi is first translated to English and then the English output is fed to the English Malayalam model to generate the Malayalam language output. So what you see here is in this pivot translation approach, there are multiple decoding steps. So we have to decode twice and there are multiple translation systems involved. On the other hand, with multilingual NMT, we have this opportunity of doing zero-shot translation. That is, without seeing a single example between the two languages Hindi and Malayalam, which by the way are both languages in the Indian subcontinent, we can directly translate between these languages. So here, as we have seen in the previous discussion, we can train a single many-to-many language translation model using just English-centric data. So English to X and X to English. And once we have that many-to-many model, it's now possible to translate directly from Hindi to Malayalam. So note that we have no parallel corpus between the two languages, yet with a single decoding step we can do this translation, and within a single translation system. So we do not need a translation system for every pair of languages. So this opens up interesting possibilities. So let's briefly look at pivot translation before we move to the other methods. So pivot translation can be either using a bilingual pivot, where I mean that each leg of the translation system uses a bilingual translation model. So there is a Hindi to English model and an English to Malayalam model in the example we just discussed. We could also have a multilingual pivot model. So what this means is that our many-to-many model itself can serve as a leg of the pivot, but instead of doing a zero-shot translation, so we use the many-to-many model to first translate from the source language Hindi to the pivot language English, and the English output is then again fed to the many-to-many model to generate the Malayalam model. Generally, multilingual pivoting seems to outperform bilingual pivoting, and the pivot translation method that we just saw is a very strong baseline for translation between unseen languages, although it has a few limitations that we just saw. So we have to have multiple steps of decoding, so errors will cascade through the pipeline. So the source to pivot stage will introduce translation errors, and this erroneous output is fed to the next stage. The decoding time is also double in the case of two-step decoding, and if the path length is longer, so if you have to go through multiple pivots to translate from a source to target, the more the decoding time. So we can reduce the cascading errors to some extent using n-best translation lists, and then re-ranking the output, combining the scores from different stages. However, zero-shot seems to offer the possibility of overcoming this problem, because there is only a single decoding step, no cascading errors can possibly happen, and you only need a single translation system. So what could go wrong? Well, it turns out naive zero-shot performance actually significantly lags behind pivot translation, as you can see in some of the results on the screen. And if you delve into what is happening here, the translation model, the many-to-many translation model trained on English-centric data, is actually generating output in the wrong language. So, for example, here, when asked to do German to French translation, 60% of the time the output is French, but in the rest of the cases, it's either English or it's just copying over or generating a German sentence. So what's happening here? So there is a correlation that is getting established between the input representation, the encoder representation of a language, and the target language being generated. Okay. So why is that happening? When we train the many-to-many model, it always sees that whenever a language, a non-English language is the input, the output is always English. So that's what the model has always seen. So irrespective of what language tag is provided, the model tends to generate English. Or it's confused, it can just copy the input. And if you sort of remove these cases where the wrong language is generated and evaluate only the those sentences where the output is in the correct language, then the performance of the zero-shot translation system seems to match the performance of the pivot baseline. Further, what is interesting is that code mixing is very rare. So once the translation model starts off by generating the first word in a different language, the rest of the sentence is always in the wrong language. So code mixing rarely happens. Now, one obvious way to sort of control this is to have methods which control the vocabulary construction. Okay, so one thing is, okay, we know that these are the vocabulary items in the target language. So the decoder during inference restricts the output to only the target language vocabulary items, and this does improve performance over the baseline zero-shot translation system. The other approach is to tackle the problem of vocabulary capacity. So typically these models are trained on jointly across multiple languages with the vocabulary being jointly learned using subword segmentation methods like BPE. And in this case, some languages may get an unfair representation of the vocabulary space, and since English is always involved, the English vocabulary might be very large. So one solution is sort of to learn the to define capacity for every language and learn subword vocabulary independently for every language involved, but then finally merge the model vocabularies. So there may be some overlap across the vocabularies of different languages, which enables multilingual learning, but every language is assured some capacity in the vocabulary, and this seems to work well. It gives a very good improvement over training with a vocabulary that is jointly learned. Both these methods can prevent generation of wrong language, but the performance still lags the pivot baseline. So what do we still have to do? So recall that we saw that the encoder representations that are generated by the multilingual model do show clustering in the form of encoder representations of different language families being clustered together. Now, this has a bearing on the wrong language generation, right? So the German part of the encoder space will always tend to generate English because that's what it has always seen. The French part will also tend to generate English because that's what is always seen, irrespective of what target language you ask for. But the English part of the encoder subspace can generate multiple languages. So if we can do a better job of generating encoder representations, ensuring that representations of different languages converge, which should ideally be the case in a multilingual system where we say that the encoder generates an interlingual representation, then the model will be able to generate the correct language. And better transfer can also happen across languages. So to this end, one approach of doing this is to kind of generate a representation for the encoder for the sentence output from the encoder, say by max pooling or mean pooling, or taking the last year of the encoder in case of a RNN encoder, and then adding objectives into the multilingual NMT training pipeline in order to ensure that parallel sentences sort of converge to similar sentence representations on the encoder output side. So this can be done by adding either unsupervised objectives which try to ensure that the distribution of encoder representations of different languages sort of match each other. This can be done by domain adversarial laws. But in our case, we actually do have parallel sentences. So we have English to some X language pairs, right? In every mini batch, that's what we are training. So the additional objective can just be to minimize the distance of the representations for these two languages for every sentence in the batch. And we could use different kinds of distance functions like cosine distance, Euclidean distance, or correlation distance. Many of these have been tried in the literature. And with this approach, we can see that the performance of zero-shot translation improves, and it is now competitive with pivot and improves significantly over the baseline multilingual NMT approaches. Now, one observation here is that the encoder representation that is generated in order to minimize the distance is kind of an approximation, because we are doing some sort of pooling. What we would ideally want to do is that the input to the decoder at every time step for different languages should be the same if the inputs are parallel sentences, because the decoder at every time step is generating the same word for parallel input sentences, and hence the decoder representations, input representations, which means the attention context vector should be the same. So that's one way to approach the problem, which looks elegant, and this work kind of takes that approach, and they show that there is improvement over just minimizing encoder divergence. And we can sort of generalize this more to say that we want to force the distance between the encoder representations at every layer in the representation difference at every layer in the decoder to be minimized. But obviously, like it's not desirable to have uniform representations across all layers of the decoder. The next method actually tries to say that given two parallel sentences, say in German and in English, if you ask the system to translate them into a third language, French, the outputs of both the inputs should agree, because both the inputs are the same in different languages, so their outputs must agree. So this method is also competitive with the pivot method, and it doesn't result in any loss in the supervised, which is the English centric or bit centric directions. The next natural question to ask is how many languages do we need to train to get good zero-shot performance, and what should be the corpus size of the languages being trained? So there is some analysis to show that zero-shot performance improves with the number of languages. So going from a 5x5 multilingual model to a 25x25, 75x75, and so on. So we can see that the translation performance sort of increases. On the other hand, zero-shot translation probably works well only when the multilingual parallel corpora is large. The next point, which to briefly mention, is this interesting area of pre-training. So there is a lot of work recently on multilingual pre-training of sequence-to-sequence models, and the question is now, can this pre-training help zero-shot translation? So the pre-training is typically done with monolingual data with some sort of denoising autoencoder kind of objective. So we could have an interesting scenario like, okay, we have a high resource language pair like Hindi English. Can we use that and translate? Can we use that parallel corpus and translate from, say, Nepali to English, for which we have no parallel data? So this is slightly different from the pivot scenario, but what you could do in a pre-training scenario is that we could pre-train a network with Nepali, Hindi, and English with monolingual data, and then fine-tune the parallel corpus with Hindi-English parallel corpus. And now zero-shot translation from Nepali to English works much better than just the standard pre-train, the standard train on Hindi-English parallel corpus followed by fine. Just that is not good enough. So the next question we look at is zero-shot translation. So let's see how it is different from how zero resource translation is different from zero-shot translation. So in both these cases, we have no parallel corpus between the unseen languages. However, there is a difference. So in the case of zero-shot translation, during training, we don't do any specific training for any particular unseen language pair. We do have additional objectives to minimize encoder representation distances, etc., but that's not geared towards improving any particular zero-shot translation direction pair as such. However, in the zero resource translation case, there is a subtle difference that the training does take into account unseen language pairs of interest and may do some additional training objectives to cater to that. For example, use synthetic parallel corpus, which we'll just discuss on the next slide. So as I just mentioned, one way of doing zero-shot translation is to use synthetic parallel corpus. So how do we do that? So we already have a many-to-many model trained on English-centric data or Brit-centric data. And how can we expose the model to many-to-many to zero-shot directions? So we can just use the trained many-to-many model to generate training data for the zero-shot direction using back translation. That's one way. But you can also generate, the problem with that is that the many-to-many performance, the zero-shot performance is anyway bad, and hence the back translation quality may not be that good. On the other hand, we can also use the pivot language for generating the synthetic data. So we have data for language, parallel data for language Y to E. So we can just translate the E side of the parallel corpus to the language X, and the E to X translation performance is better on the many-to-many model, thus creating Y to X synthetic data. We could also use monolingual E data and use the E to X direction translation systems to generate synthetic source as well as target sentences for the languages Y and X. Of course, the quality of this methodology depends on the quality of the underlying translation models, and we can think of iterative refinement schemes where we start with an initial model, create back translated data, augment the model and retrain the MLMT model with the back translated data, and repeat the process till we see improvement in the translation quality, and we get improvements in translation quality for a few iterations. So a different take on the same basic idea are methods which use iterative reinforcement learning approaches, where the basic training is still done in the original translation directions, but then there are reward functions which are dependent on performance of in the zero-shot directions, which is measured using reconstruction losses and language modeling. But the problem with back translation is that if there are many languages involved, if you have a 50 cross 50 language multilingual model, you would have to generate a lot of back translation data in 50 square language pairs to be able to address all the zero shot directions. So one work kind of looks at the problem in a random online back translation way, where what is done is that during training with the standard English-centric data, for every sentence pair, we generate one non-English sentence pair on the fly using back translation and augment the batch with that synthetic data and optimize. So what this means is it effectively doubles the corpus size. For every original data, you have one synthetic example that is generated. This helps to scale the training process to a lot of languages, yet the results sort of approach the pivot baseline. Finally, we can do student-teacher training. So the idea here is that we want to train a system between the source language and the target language, for which we don't have any parallel data, but we can train a pivot to target translation system, and then using standard cross entropy losses, and then train a student to a source to target model, which is the student model, to follow the distribution of the parent model, which is the pivot to target model. Roughly what you would do is we start with the pivot target parallel corpus, train a pivot target model using standard maximum likelihood estimation, then take the source to pivot parallel corpus and use the pivot target as the teacher and do student teacher training. So one way to do that is sort of take the pivot side of the data of the source pivot data, translate it using the pivot target model to create source to pivot synthetic data on which now a translation model is trained. So this is a standard way to do knowledge distillation for sequence-to-sequence models. Finally, so far we have looked at scenarios where there is a single bridge language involved. Most cases this tends to be English. However, and the assumption always was that it's very difficult to find data in directly between non-English language pairs. But there is some recent work which is interesting, which shows that we could probably look at multi-bridge systems where we have corpus directly between non-English languages. So the question is, how do we acquire such parallel data? Is there enough parallel data of that sort? And if we have that, then how do we address data imbalance? Which means that even if we do gather non-English data, most of the training data in the multilingual training setup is bound to be English-centric. So how do we address that skew? And how do single bridge, which is MLMT systems with just one bridge language, English, compare with multi-bridge systems? So let's look at how we can mine this data first. So one way to do that is to take a lot of monolingual corpus across many languages, and for every pair of languages mine translation pairs. Now this is obviously expensive. You can mine using your favorite method, say laser, labs, etc. But it's expensive to kind of look at all sentence pairs in all the language pairs. So we look at this work looks at what is the most promising language pair to mine from. So obviously you would want to mine from English to other languages where you have most chances of mining data. But in addition, we can cluster languages by the language families, and then within every cluster we would mine languages, because it's likely that these are languages which are in contact and they share some parallel corpus. Or the next method is within every cluster we select a few bridge languages which are typically high resource languages in that cluster, and then try to mine parallel corpus between the bridge languages in different clusters. And it's likely that there is parallel corpus between such languages. For example, the UN proceedings are translated into Arabic and French, so you're likely to find parallel corpus between at least these languages. The other very simple way to extract data is to use the existing English-centric parallel corpus. And it turns out that a lot of this English-centric parallel corpus is actually sourced from a lot of multi-way parallel corpus like European parliamentary proceedings. So if you just pivot through English, you will discover translations between non-English languages also. So what you see on the left bottom is some stats from WMT data for a few languages. So the gray cells are the English-centric data sets, which are like in the order of tens of millions of sentences. But through this simple pivoting process, we are able to discover a decent amount of translation data directly between many language pairs as well. Non-English language pairs, and this applies not just to WMT, which may have a lot of Europal sources, and therefore you are likely to see this kind of data, but even on a lot of parallel corpus crawled from the web, as you can see on the right hand side. So even those corpora do have direct translation data between a lot of language pairs. Now once you have this kind of a language pair, how do you sample from this? The standard way to address data imbalance in English-centric datasets is to do some sort of temperature-based sampling. However, given the large sample space, you have to mine from a quadratic number of pairs. This may still be English-centric, and the sampling may be biased in favor of English. So for example, in the WMT set we just saw, just 15% of the sentence pairs are exclusively non-English, and hence the sampling will still have a larger representation for English. So there are a couple of solutions that have been proposed. So one solution is to say that just do a temperature-based sampling based on the marginal distribution of the target languages first, so that you have sampling based on the distribution of the target data, and then sample the source language uniformly. The second solution is based on the same motivation but takes a more principled approach. So we sample from the probability matrix of distribution of the language pairs while ensuring that the source and target marginals follow a temperature based schedule. And both these approaches have shown improvement over the standard temperature based sampling for non-English directions. So to summarize the results in this multi-bridge scenario, when we add non-English centric data, we obviously see a good improvement in translation problem performance for the newly trained directions. But surprisingly, even the zero-shot directions now improve because the model is now exposed to not just translations into English, but also into a variety of other languages. So it's generalizing in a better way. The other takeaway is that multi-bridge translation does not adversely impact the English-centric direction, so that translation quality is maintained. If you combine multi-bridge translation with synthetic data augmentation, we do get complementary benefits as well. However, one thing to note is that while the blue score gains look good, some human evaluation shows that the gains are not as significant. And there is really a lack of good evaluation sets in many of these non-English directions. So there's a word of caution to be taken when you look at these results. So with this, we conclude this look at the section on low resource translation with MLMT. And to summarize the takeaways from this part of the tutorial, so we can see that Multilingual MLMT has helped make significant advances in low resource machine translation, particularly from novel methods that have come about in transfer learning and zero-shot translation. So on the transfer learning side, what is key is that we optimize the right objective for improved transfer, and language relatedness plays a key role in successful transfers. How do we design the models and the pre-processing so that we can take advantage of that is important. Transfer works better in a many-to-one setting compared to one-to-many setting. So there is scope for exploration as to how we can improve transfer in the one-to-many setting. Lexical transfer is easier to achieve than syntactic transfer. So again, there is scope to see how we can improve syntactic transfer. Coming to transfer between unseen languages, so pivot translation is a very strong baseline to beat, and zero-shot translations face the problem of having this spurious correlation between the input representation and the output language, and this can be overcome by reducing the divergence between internal representations of different languages, or by using multi-bridge systems. We can also use zero-resource translation, which use synthetic data to reduce spurious correlations. So with that, we conclude this part of the tutorial, and I will hand it back to my colleague Chen Hui to go through the next.
Okay, from now on, I'm going to talk about the last use case of MLMT, which is multi-source translation. First, about the motivation of multi-source MT. Why? Let's first look at the standard bilingual corpus. So in this corpus, we have English and French sentences aligned. And in the multi-source schedule, we may have another language. Let's see, it's Spanish. And for the parallel English and French sentences, we have another Spanish sentence. That is a translation of the English and French sentence. All these three languages, they are parallel, they are aligned. So why this kind of corpus can be useful? So let's consider about a scenario. Let's see, in the United Nations, documents are first written in English, and we have already translated them into let's see, French. And next, we also want to translate them into Spanish. So in this case, the previously translated French sentences can be used to assist the process from translation English to Spanish, right? So, and this scenario exists not just in the United Nations, but also in EU, right? And we're first going to look at the case that we have a complete multi-source corpus, and how to improve the translation by using this multi-source corpus. And the first approach being proposed is called the multi-source encoder approach. So here we have two encoders. The first encoder is for English, and the second encoder is for French. And we want to use them to improve translation into Spanish, right? And their approach is that they combine these two source encoders, they are representations of the source sentences in two languages, and then used the combined representation to initialize the decoder, then to do the translation. That's why it's called multi-source encoder. And let's see how it works. So here shows the results reported in this paper. And we have two systems. So the first one is that just translate using French English and German English separately. So not multi-source, just single source. And that's their result. And this is by combining them, by using multi-source method. And we can see that improves a lot. And in their papers, they also compared different ways to combine the multi-source. One method, they call it child sum, and it also works well. And they also tried multi-source attention, so not just the final hidden state of the encoder, but they also combine the attention by different ways. And we can see that the improvements are much larger. And the second approach has been proposed for multi-source available case is ensembling. So here we have a decoding state, and because we have multi-source, so it can be translated into different states, right? So we have different states, and then we have a gating network to give weights to each source language. So to give weight to each source language for our ensembling. So we have different sources and weighted by this gating network, and finally we use these multiple sources to get this the final output. And how it works. And here shows the results reported in their paper about the ensembling method for multi-source translation. And we can see that these are the single source, and this is multi-source. And again, here they compare different combination ways for the ensembling, right? And we can see that, so here the context dependent ensembling shows better performance compared to the single model. And they also tried on different languages, and the final experiment is that they combined German English, French English, and then translate to English, right? And we can see that they got a very good improvement by using the multi-source ensembling. And the last approach that I want to introduce is called the concatenation. And this approach actually is a very simple approach. What is being done here is that, let's see, we already have a multi-source corpus, and we concatenate all the sources here. See, this is all the sources, right? We concatenate them together. So hello, bonjour, and etc. And let's say our target language now is Japanese, is konnichiwa. And we combine them together, and we train a vocabulary on this combined source and target corpus, and then train a system. So this is just simply concatenate the multi-source and do multi-source translation. How it works? So in this paper, it compares with the ensembling and multi-source encoder approach actually. And in various settings like French, English, German English, and or foreign language, and in Arabic English as well, and also Spanish English as well, we can see that surprisingly, although this multi-source approach is very easy, right? It's very simple, but it outperforms the ensembling methods and the multi-source encoder methods. Okay, so this is a case when we have a complete multi-source corpus, but we also may have some scenarios that we only have incomplete multi-source corpus here. So only a part of the Spanish sentences has been translated into French and English, but we have missing parts here. So in this case, how to utilize this Spanish corpus to improve the translation into French? And in this paper, the authors proposed two methods. The first method is very simple, which is, you see, just using some symbols like no, because this is missing. We added no, and then do multi-source translation by using a multi-source encoder. And another way is that they do data augmentation. Let's see. We first train a multi-source MLMT system by using the English and this SK language, because we have a part of this Spanish, this CS language as well, right? So we can create a multi-source translation system to pursue corpus, right? To produce a pursue corpus, then use this pursue corpus to translate again. So that's the way of the missing source sentences approach that's proposed by this paper. Two approaches, and let's see how it works. Here again show the example. So we have the baseline models, which is first the one-to-one, just one language, and also the multiple encoder and filled by the null symbol, right? And it also compared with the back translation method. And this is the proposed method, which is the data augmentation method. And we can see that they also propose different types of data augmentation: fill in, replace, and fill in and add. And we can see that the data augmentation method works best in this multi-source incomplete scenario. Okay, at last, let's do a summary of this multi-source approach. And we can see that in the case of the vanilla method, so they need an n-way corpus, right? And this is multi-source method, so multiple or shared source encoder can be used. And the concern is that because you combine the multiple encoders, so the training times will become larger. And the good thing is that you can explore the n-way corpus very well. And the second approach is the ensemble approach, right? In the ensemble approach, the solution is the ensemble, the multiple bilingual models. And the concern is that how to learn the ensemble function. In this case, we need a small n-way corpus. And the benefit is that we can reuse existing bilingual models. And the last one is synthetic data, so a data augmentation method, which can help to generate the missing source sentences. The concern is that this is not feasible in real-time translation, because you first have to generate the pursue sentences, right? But the benefit is that if it's in the case of post-editing, it might be applicable. Okay, so that's all for multi-source translation. So at last, I want to talk about the data sets, future directions, and finally wrap up this tutorial. So about data sets, again, I summarize it by doing the, I summarized it by the user cases. So first, user case is Multiway. So for Multiway datasets, actually we have a lot of datasets. And here I summarize the existing Multiway datasets, categorized them by languages. So for example, if you are interested in European languages, there are a variety of resources, parallel corpora are available, like the Europol, or the JRC, the DGT, etc. So you have a lot of resources. And if you are interested in Asian language, actually we are organizing the WAT shared tasks. So this is workshop on Asian language translation. So in there we have a lot of Asian languages, including Japanese, Chinese, Korean, and Indian languages, South Asian languages, etc. And if you are interested in Indic languages, we also have a pretty good corpora like listed here. And recently, massive corpora also have been released by Facebook, etc. So here, for example, some representative ones are the Wiki Matrix or the JW300. So it contains more than 100 languages. So, which is a very good resource for you to, if you are interested in massive MLMT study. And we also have others, like the United States corporas, or the TED corpora, or the Opus subtitles, etc. And actually, you can refer to categories like the open source corpus project, or the Indic Net catalog for a more comprehensive lists of paracorpora resources for Multiway datasets. Next is about the low resource or zero resource Multiway datasets. Here I listed a few of them and categorized them by the domain and language. And we have the corpus called the FLORAS, which is a Wikipedia corpus domain. Wikipedia domain corpus consists of English, Nepali, and Shali. And we also have a corpus, the XNRI, which is image caption dataset. This corpus contains 15 languages, but very low resource. We also have general domain corpus for 10 Indian language corpuses, 10 Indian languages, the CVIT corpus. And also another Indian corpus, which is a Wikipedia domain consisting of 6 Indian languages created by crowdsourcing. And if you are interested in the WMT shared tasks, they also organizing some raw resource or zero resource shared tasks. For example, this one, which the domain is web, and they have German and Upper Slovenian as a language. Of course, you can use all the Multiway dataset listed in the previous slide. Can be used for this setting by using like a small set of them, right? Just using a very small set of them, you can treat them as a raw resource setting. And at last, about the multi-source datasets, I also try to list a few here. And the first one is Europe, which is Europol. This is a very famous corpus, right? So this is a 11-way corpus, and the domain is politics, and it contains the main European languages in the EU. Second one is TED corpus, contains 5 languages, and the domain is spoken language because it's TED Talks, and it contains 5 languages like French, German, Czech, Arabic, and English. And the third corpus is a United Nations corpus, which is a 6-way corpus, and the domain is politics. And it contains the official languages in the United Nations, which is Arabic, Chinese, English, French, Russian, and Spanish. We also have the ILCI 11 way, which is tourism and health domain. It is Indian language plus English. And this corpus is also very interesting. It is the Asian language tree bank. You know, this is a tree bank and containing 9 languages, and domain is the Wikinews domain. And it contains most of the Southeast Asian languages plus English and Japanese. The most massive multi-source data set is the Bible corpus. This is very big. It contains 1,000 languages, and the domain is about Bible, so religion domain. So most major languages are contained there. So these are all good resources that you can use for multi-source machine translation study. Okay, so after a discussion of the data sets that you can use for MLMT, finally I want to do a discussion about the future directions for MLMT. So we just try to pick up a few, but more of your ideas are welcome. I mean, your ideas are more welcome to for the contribution of these future directions. So the first future direction that we think is promising might be how to explore pre-trained models such as BERT or multilingual BERT, etc., to improve the MLMT performance. You know, the pre-trained embeddings or encoded decoders have been should be useful for MLMT. However, there are still some issues, such as first, how pre-training can be incorporated into different MLMT architectures is unclear yet. And another thing is that pre-training usually is used for fine-tuning a task, right? And for the case of MLMT, so how to address the techniques to minimize impact of transfer in fine-tuning to improve, for example, raw resource or zero resource or zero-shot MLMT it still remains an open question. And we think that unsupervised pre-training and unsupervised MLMT might be interesting directions that worth investing further. And the second future direction we are considering about is about the unseen language pair translation. So previous work on unseen pair language pair translation, they only address the cases where a pivot language is related or shares the same script with the source language. But in reality, the pivot language is unlikely to be related to source or target languages. And in this scenario, I think, which still requires more and more investigation, especially in the case of zero-shot language, that there's no parallel corpus between two languages, right? And the last thing is that, as you have already seen in the previous part introduced by Anu, you see, currently still a simple pivot baseline works best, but this must not be the case. So I think new approaches are needed to be explored to improve, to outperform a simple pivot baseline. So that's the things that we're considering about the case of unseen language pair translation. And the third one is which we think interesting is about joint multilingual and multi-domain MLMT. You know, not just languages. We have several thousands of languages, and many of them are raw resource. That's true. But even for each language or for each language pair, we all still can have tens of domains or more than that you are interested in, right? And for each domain, again, you are not supposed to have enough data, right? So how to combine multilingual and multi-domain jointly? How to do multilingual and multi-domain MT joint learning? I think it's a very interesting problem. And transfer learning in this case of course, it's very interesting in the case of domain. So we want to improve the domain, the raw resource domain, right? By doing transfer learning or domain adaptation. But in the case of multilingual and multi-domain, our transfer learning strategy has to span both language and domain. So this is very challenging, right? And we think that it might be interesting to explore the adversary approach where domain and language invariant representations can be learned. So if we can learn domain and language invariant representation, then transfer learning can be done much easier. And the last future direction that we want to talk today is multilingual speech-to-speech MT. This can be a very interesting direction to explore the multilingual speech translation. And whereas ASR translation and TTS modules can be multilingual. I think today we have speech translation, but speech translation is speech to text. And usually it's not multilingual, it's just bilingual. So multilingual speech-to-speech translation is really, very challenging, I think. And where the interesting challenges and opportunities there may arise in the request to compose all these multilingual systems into an end-to-end method. So how to learn an end-to-end multilingual speech-to-speech system? Obviously, multilingual end-to-end speech, it requires training data of multilingual speech-to-speech translation, right? And which will be very sparse, very low resource. So how to learn it in an end-to-end way? How to do transfer learning? How to do this? How to address this like zero resource or zero shot setting would be a very challenging scenario that we can explore. And I just mentioned about a few future directions that we think are interesting to explore in the future. But as I said before, so your ideas are more welcome. We hope that this tutorial can give you insights and the research community can join together to explore more interesting and more promising ideas or approaches to further promote the research of MLMT. All right, so finally, let me wrap up this tutorial. So in this tutorial, we give an in-depth, very detailed explanation about MLMT based on their user cases, which are multi-way modeling, raw resource translation, and multi-source translation. And the core issues for multi-way modeling are parameter sharing, language, divergence, and training protocols. And for raw resource translation, they are transfer learning, zero-shot modeling, and zero-resource modeling, right? And we discussed all the challenges in these use cases. And we also compared the strengths and weakness and the remaining problems in these user cases. And we hope that this tutorial can give you a fundamental understanding of the current research progress in MLMT, so that more researchers, more students, more engineers who are interested in this domain, in this research field, you can join us and let's promote the future of MLMT research together. So that's it. So finally, I want to thank you all for watching our tutorial video until the end. And here shows our email address. So if you have any questions related to our tutorial, please contact us. Feel free to contact us. And I want to remind you that our tutorial materials can be found in this website. And we also have a survey paper which summarizes the recent MLMT works. So thank you very much. Thank you all.